Welcome everyone. Thanks for joining us for today's webinar. My name is Shule Tatar. I am the Digital Marketing Manager at NOPSEC. NOPSEC is the leading provider of vulnerability risk management and penetration testing. Today we are presenting Password Playground presented by Shawn. Just a little housekeeping before we get started. If you have any questions during the presentation, please type them into the question box on your WebEx control panel. I will bring them end of the presentation, and this webinar will be recorded. Now, without further ado, we will turn over time to Shawn, our presenter today, NOPSEC head of the security research. So, Shawn, stage is yours.
Thank you very much, Shula, and thank you everybody for attending this webinar today. As she mentioned, today we're going to be talking about our password playground, and this is really just a statistical analysis of passwords and character distribution within them. So my name is Shawn Evans, as Shula had mentioned. I am the head of security research here at NOPSEC. I have roughly 12 years of experience in the offensive security realm, performing pen tests of all manner across mobile devices, internal, external networks, and unlimited web applications. So lots of different things I got to hack into over the years. I have also created a number of tools that have contributed to the offensive security community that are all available on GitHub, so feel free to access any of those. So today we're going to be covering passwords, but it's really about how you store passwords securely, which is called a hashing algorithm. How, as a hacker, I reverse that hashing algorithm and crack that password to resolve it to its clear text component. And from there, we're going to look at what the character distribution and frequency trends are within passwords that we crack to see if we can identify patterns that might aid us in cracking more passwords. And once we get to that point, we have a list of cracked passwords. We want to kind of analyze what the context, if context impacts the way the password is formed or the complexity requirements. And from there, we also want to investigate which hashes are going to be most difficult for a hacker to actually crack in a real-world setting. And then finally, just to see what's next, like what are the takeaways, where do we want to take this research? So getting right into it, hopefully everybody on the line that is managing a web application is familiar with what a password hash is. And a hash is really just a way to encrypt, a one-way algorithm to encrypt a password effectively. It prevents the clear text access of the password, and that's why a hash is advantageous. So for the example, if you have a SQL injection vulnerability and an attacker has gained unauthorized access to data in the backend database, you don't want them to be able to just access everybody's password in clear text, so you hash it, and it's a good security practice to do. But that's only half of the picture, because the security community basically recommends that all passwords are not only hashed, but a salted hash. And a salt is really just a value that you prepend or append to a clear text password to then compute the hash of that value rather than just your password alone. And what this does is has the effect of increasing the password complexity even if you might have a weak password. And it just increases the randomness and the entropy, makes it more difficult to crack, more difficult to compute. So when we talk about these different algorithms, one of the things we'll touch on is computational complexity. And the more complex an algorithm, the more time it's going to take to compute, which equates to slower time to crack, because that's kind of factored into it. I have to go over this algorithm millions of times, and that goes into how long it takes to crack, which is the other consideration is performance. So if you do have, a hash that might take a second to compute, that's going to be a performance hit versus something that takes 1/100th of a second. So, you have to have a balance between computational complexity and performance, because, if you have 1 million users logging into your web page a day, like Amazon or Google or something like that, you're either going to need a lot of servers to do a complex hash, or you're going to have a hash that is more suited to the environment that it's going to be, used in. So if you don't have the computing capacity of Google, then there are other considerations. And just to show you an example of what we mean, what a hash actually looks like, you can see a simple MD5 hash example of the password 1234, and it equates to the 32-character hex string that you see beside it. So that's what a hash is, and that's what, as a hacker, we try to crack day in, day out when we gain access to, domain controllers, web application databases, whatever the case might be. So when we talk about password cracking, it's the act of reversing a hash to its clear text counterpart. So it's not really encrypting anything because there's no two ways about it. The only way to get to the value of the hash is to just find what it was used to calculate it. It's a one-way function. And when we talk about cracking, there's a few terms that we're going to see throughout the webinar that we should become familiar with. And the first is brute force. So this is just a method of cracking a password. And what it means is that we're going to exhaustively try every possible character in every possible position to, calculate every permutation of a password in a given key space. This is really good if you want to be thorough, but thorough is also very slow. So this might not be the best tactical method to use if you're out on engagement. The second method that we're going to refer to is dictionary-based. And this is when we have a list of words in a file. So it's a pretty simple text file. And what we can do is then take each of those words, compute the hash that it would be equal to, and compare that to the thing we're trying to crack. And if they're equal, we know we found a match. So this is much, much less deep than a brute force attack because it's not exhaustive. So I might miss a lot of things, but I might guess, all of the common passwords, such as like password 1 or winter 2018 or something like that. And one of the things that we combine with a dictionary-based attack is called a rule. And this is available in both John the Ripper and Hashcat, two very popular cracking programs that you can download. A rule is simply just a programmatic way to change a password in a dictionary. And, it could be something very simple, such as appending a digit or a special character. And it can get more complex, like appending 4 different characters. So using Hashcat as an example, it has a number of different rule sets, one of which is the best 64. It's roughly 64 of the most commonly occurring permutations that you might find in a password. And what's nice about this is you can take a very simple password. Let's use the word password as the example. And using this rule, that effectively turns that one password into like 64 different passwords or permutations of that word. And they have even more complex rule sets that have up to 32,000 different rules, or 32,000 independent permutations of a password. So you can see how a very simple dictionary could grow to a much more significant complexity by using these rules. So it's a really nice hybrid attack where you can do more than just your dictionary would otherwise allow. So that brings us to a mask. And a mask is used in conjunction with a brute force attack, but it's a way to define a key space per character to limit the possible number of permutations. So it's not as exhaustive. It's basically just saying, okay, we're confident that the pattern of a password is going to be, for the example here with the mask, it's question mark, upper for you, lower, 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 digit, 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 digit. And this would translate to something like task 1, 2, 3, 4. And, it would also be a lowercase m, like mass 1, 2, 3, 4, or something like that. But the passwords that are going to be brute forced have to fit into this mask or this pattern. And finally, we have a character set. So if you use the example in the mask above, a character set for uppercase would be all of the uppercase characters from A to Z. Lowercase would be lowercase characters from A to Z, digits 0 through 9, and special characters are, just basically everything on the number keys, maybe a few more on the keyboard. But that's what the key space is. So when we talk about a character set in the context of cracking, the greater the key space, the more complex the password and the harder it is to crack. So if we can limit the key space to say, okay, well, we're pretty confident that people don't use the letter Z or the letter Q in their passwords, we can eliminate those from our key space, and it makes cracking that password in the brute force method much more effective. So that's why it's really cool and important for us to understand what the key space is and how to minimize it as much as possible while still giving us the ability to crack passwords. So that brings us to the character distribution in passwords. And this is really the question that we had when we approached this, because if anybody attended the previous presentation we did on passwords, it focused more on just the best practices, touched lightly on how to crack things in that, but this is really the deep dive. We really wanted to take a look at, okay, well, we've done a lot of, 12 years of offensive security experience. I had the opportunity to analyze a lot of real-world password dumps, and I wanted to understand basically what the probability that a specific character would appear in a specific position within a password. There's more complex ways to do that than what we have in this presentation, but I have to brush up on my linear algebra to get answers to those kinds of questions. But we're getting to the point with these tools that we have. So that's the neat thing that we want to be able to do. And we then want to take the information once we get those statistics to see, well, now that we have these, what information about probability to inform password lists, masks, key spaces, those kinds of things. And finally, we wanted to figure out how this actually impacted the efficiency of a brute force attack. And, you know, as we said, to answer all of these questions, there were tools out there that kind of touched on some of this functionality and probably answered them independently. But the best way to learn is to do something on your own. So I'm a big proponent of DIY development. So we've developed a tool. This introduces you to Panalizer, Password Analyzer. It's very simply just consumes a list of words and will tell you the frequency of characters in certain positions with a fixed length password. So all of the passwords that we compare are all going to be the same length. So 8 to 8, 10 to 10, 9 character to 9 character. And then based on that frequency analysis, we can generate statistics that then aid in generating password masks and new character sets. And this is all a little bit abstract, so I think the easiest thing to do would be to show you a quick example of how this works. So you can see on this screen, hopefully, the demo gods never really let these things work out. But you can see it, okay, good deal. I'm using a password list called cracked all time. So one of the things we kind of squirrel away when we do dump a domain controller or something like that, we remove context, but we're saying like, okay, these are live passwords, these could be valuable in the future, we're going to save these lists. So that's what we have here in the cracked all time list. And what we'll do is just quickly show you the distribution of the characters within this password list that we have here. So we'll do a -R and boom, there we go. So we can see from this that the most commonly occurring character in an 8-character password would be, looks like uppercase. The entire first column, if you see there, let's see, these guys right here in this first column, all uppercase. So there's a really good chance that in an 8-character password, based on everything in this password list, that you're going to have an uppercase character in that. And we have an easier way to digest that. This is kind of just like really debug output or just interesting statements that we wanted to look for. But let's say we wanted to compute a mask in the same way that we could do the upper, lower, digit, special kind of a thing. And Panalizer will help us with that. So we can see from this that it correlates pretty well. We can see an upper, lower, digit. So that's probably going to correlate to the most commonly occurring pattern that we observed in the password. So this is all very helpful. And finally, we can do the custom character sets even as well with a -K argument here, which is key space. Okay, so this is going to parallel the results of mask, but you can see in this column here, like this string right here, this defines a new key space, and you might notice that it does not include all of the letters of the alphabet, because based on the analysis of these cracked passwords, the top 10% of this list comprises only of these characters. So this would significantly increase the efficiency of a brute force attack, because now we have a reduced key space, and we can tell from this that also the top 10 percentile, it doesn't even have any special characters. So that's, again, a further reduction of the key space. So this is what Panalizer does and how it's going to be useful. So with that in mind, let's take a look. If password context matters. So what we did after we developed Panalizer and we finally figured out that it was working, we analyzed passwords from popular password dumps to see if the password context influenced the complexity and the character patterns we noticed. So for this, we have a number of domain dumps that we have archived locally, but thankfully the internet provides everything you need these days. And it's actually, all of these lists were gathered together from GitHub, so you can go look at these things as well. But we have Windows domain dumps, so this is just all of the NTLM passwords from domain controllers that that hackers have dumped throughout the years and then uploaded to GitHub apparently. We have an alleged Gmail password list. And then Ashley Madison, this was a unsavory site, but it was a really great example of live web app passwords. So that's why we have elected to use that one here. And finally, we found a university dump, which was, universities have one of the most complex domain environments that you can imagine. If you have a school with 20,000 people, there's 20,000, or there's probably 5,000 new people added to the domain at least every year. And usually they don't remove them in time. So these are the largest domains I've ever analyzed. They've been at schools, something like 1.5 million users. So it's an interesting list to digest. And finally, because this is, we have to do some controls in this, we wanted the minimum length to be 6 characters and the maximum length to be 10 characters, because this is pretty much within the feasibility of what you can accomplish in a brute force guessing attack. And we use the top 2 patterns. So if you remember back from the list, just the top 2 of each list. And we can show you real quick just, what it looks like to calculate that. So there you go. So this is just going to be for the cracked all time. But we're going to do the same thing with these specific 4 password lists. And here's the results of that context analysis. It's actually kind of interesting because there is a distinct difference between what the complexity requirements are for things like Gmail or more generically just web applications in general. But it has to be taken kind of with a grain of salt. I think a lot of web applications these days are enforcing stronger password complexity requirements. That's by no means across the board. There's definitely a lot of prominent sites on the internet, banking sites, stock sites, that for whatever reason limit the length of your password to like 12 characters, which is just infuriating. I think most of mine are like excess of 25. So it makes it very difficult then to make a password that I feel would not be crackable under such restrictive conditions. But if you do have an application like that, you might notice that within the top 2 patterns of both Gmail and Ashley Madison, there isn't a single instance of a password that has a special character in it. So what we can derive from that is that the web applications have a reduced key space. So if you dump a web application database, there's a really good chance you're going to crack a higher percentage of the passwords than you would for a domain dump or a university. So if we look at the domain dump, we can see that once you get down to roughly, let's see, 6, 7, 8, 9, 9 character long password, we finally see the first instance of a special character within a password, and 10 also included in there in the most popular. So the key space, even for the most popular passwords, is increased. So this is going to take a little bit longer. The only saving grace about a domain dump is that NTLM hashes are relatively fast to compute, but we'll get to that later. And if you look at the university, as I explained, these are kind of like massive domains, and they all have varying complexity requirements for their passwords because they don't want to have to be continuously unlocking student accounts. But you do see the presence of special characters, so we can kind of derive that there is at least some requirement for digits and special characters, but it might not be accurately enforced because you see a lot of these things with the universities. Some of them don't even have characters in it. It's just or characters, the alphanumeric characters, so your A through Z's, and so on and so forth. But interesting results. So from this, what we were able to derive is that there's a distinct difference between domain dumps and web applications in terms of complexity, and it's probably going to be easier to crack your web application passwords, unless, of course, they're stored correctly. But what we really wanted to determine, was what the best method to crack a password is, because when we're on an engagement, we are on a time-boxed assessment. I might be on site at a client's office for 4 days, so I have to have a very tactical solution to cracking passwords that enables me to use the information while I'm on site. I can have a system running for a month off-site, but that doesn't necessarily help me if I wanted to elevate my access within an environment. So this is supposed to be an investigation into how can we get the most passwords in the least amount of time. So what we did is generate an experiment. So we have a hash list, which is about 109,000 Windows NTLM hashes, just accumulated from everywhere. But NTLM hashes come from domain controllers, and domain controllers are representative of client environments. So that's why this is a really good list to use. And it's huge, so it's going to have, diversity of passwords. So the first method we used was a dictionary method, and this is every single password in the list and rule that I have, which is substantial. We have some password lists which are, multiple gigabytes. We have some simpler ones that are down to 25 passwords. We kind of combined all of these, and the problem with this experiment is I actually did the dictionary method over many, many, many days and just kind of aggregated the results. So it's a little bit biased in that respect, but the end result is the same. The brute force method is using the panelizer to generate the character masks and use that to do the brute force testing. And like we said, we're not going to get much beyond like a 10-character password. It's just computationally feasible, and that's really the biggest benefit of a dictionary-based method. You know, a dictionary-based method, you're going to have passwords that are from 8 to 10, up to 15, up to 20, 25 characters in length. So there's nothing really stopping a dictionary from having long passwords that are extremely complex, but because it's in my dictionary, I can crack it. And the system that we performed this on was a relatively powerful laptop with an NVIDIA GPU, modern i7, 12-core processor. So it's pretty fast. It's well suited for doing this kind of work. And unfortunately, I thought the brute force would actually bag us more passwords, but it turns out that it didn't. The dictionary method in this controlled test cracked about 30.8% of the passwords, and the brute force, using 6 to 12 characters and the top 8 patterns, cracked about 12.5%. Now, we did 12 characters of this, and it did take probably about 7.5, 8 hours. But that's something, if I dumped a domain and I went back to my hotel room on a client engagement, I could do that feasibly while I'm on an engagement. So I can have those results the next day. So I felt it was representative of what we would actually do. That's not bad, but the dictionary said if you have a huge set like I do, you can get almost a little bit more than twice as many passwords cracked through a dictionary-based method. But, like I said, that was probably over a 2-week period. So if I actually did this over again, I would probably limit the amount of time that I could do a dictionary-based attack, and I have a feeling that they would be more closely aligned. The one thing we can say with confidence is that in the space of 6 to 12 characters, I got almost all of the ones that were probably 6 to 12. There might be a few stragglers, but I think it did a pretty good job at getting a majority of them. All right, so that brings us to the question of, okay, fine, you're cracking all of our domain controller passwords, but we don't have much control over the way Windows stores passwords, at least not yet. So what hashes do provide the best security, and this is more in the context of a web application, where you control how the password is hashed. So it's what password hashing method should you use in your application. And for this assessment, we used the default password list with John the Ripper. So this is about 3,600 or so passwords and many hash formats. So MD5, SHA1, 256, 512, hashing format called bcrypt, and finally NTLM, which is what is managed in the domain controller, how the Windows stores your passwords. And for this, what we basically did is took that John the Ripper password list, it's password.lst, and we hashed every single one of those words in that dictionary using a tool that we created called InfiniCrypt, because, like I said, when in doubt, build a tool. So this is just a very simple utility. It takes a string or a file as input and outputs all of the hashes that correlate to the words in the dictionary. So for this, we have a constant mask as well. So it's a top 8 mask, 6 to 8 to 10 characters in length. And we actually generated that based on the password list. So I can show you real quickly what that would look like. What do we say? Top 8, 6 to 10. Okay. So 6 to 10, and we selected 10 because it's nice and easy to compute, and it doesn't turn everything into days. So this was basically the mask that we used for input, and I believe we probably did a more complex key space one as well. So there you go. It doesn't even have any special characters in this one because this password.lst, fairly simple password list. So it was really just focusing on how long it takes to crack all of these different various hash formats. So with that in mind, here are the results of the experiment, and we also included the hash example so you can get a visual idea of what these hashes actually look like in a real-world setting. So fastest, most easy to crack, MD5. So if you're using MD5 to hash your passwords, you're not doing it right, because I was able to rip through these things in 2 minutes and 38 seconds, which is next to no time at all. NTLM would be the second easiest. It's actually a derivative of MD4, 2 MD4 hashes kind of combined together, but it's a predictable algorithm. Everybody knows how to do it. You can have hundreds of libraries that compute this NTLM hash, and that one was crackable in 3 minutes and 31 seconds. So you can kind of see for the SHA-1s, these are marginally better than MD5. But if you get up into the 256, 512 range, it becomes a little more computationally complex, but it's 33 minutes for SHA 512. That's still tactically efficient. I could rip through a bunch of SHA 512 hashes in no time at all on an engagement. And that brings us to bcrypt, which is probably the recommended algorithm for your web application, because if we didn't actually get through this, and you might notice the crack speed, when you run Hashcat, it actually gives you an estimate of how long it thinks it's going to take to rip through these and compute and compare all of the hashes. And with the GPU and everything enabled, it was 571 years, and that was only for a 7-character password. And that's just bonkers. So, it probably would more than double if you tried an 8-character password. It would probably be up into the thousands of years. So bcrypt is a very computationally intense password hash. And it is complex for a few reasons. It has a salt baked into it, so you actually have to provide that when you're calculating the hash. If you don't provide the salt, I guess it could be a null, you lose that complexity advantage. But this is definitely by far and away one of the more complex hashes that you can use within your web application. And there's a few other ones that are similar to bcrypt. Bcrypt is probably the most popular. It's what Linux distributions use. Many web applications we've attacked have used this. And really the only way to feasibly attack a bcrypt hash is to take a dictionary-based approach and say, okay, well, here's 25 passwords, run these simple rules, and we'll see if we can get the person that has password 1. So at least we can gain unauthorized access to something. But even that can take hours. So very, very slow. So the next thing we wanted to investigate was to just see how password length influenced cracking speed, because I think it's conventional wisdom that the longer something is, the greater the key space, the harder it is to crack. It's a more complex algorithm. So that complexity is introduced through two elements, key space and length, and we combine these two for the ultimate password. And the goal was to just really determine when does a password become infeasible to crack. So for this experiment, what we did is have the NTLM list of the password.lst, so the same one that we used for the previous results of the hash cracking speed. And we used a constant mask. So this is just going to be an upper, lower, 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 a digit, and a special character at the end. So it starts with an uppercase, ends with a digit and a special character. And with each iteration of the password increase, we just added one more lowercase character. So it was effectively an increase of 26 different possible permutations within that character space. And what we found is, it's not terribly surprising, but what is surprising is the jumps that you get. It's not a linear jump, it's an exponential jump. So you can see for a 7-character long password, there's the mask, it took just 4 seconds to rip through all these things. If you do 8 characters, it's going to be 14 seconds. A 9-character mask is going to take you 4 minutes and 37. And you can see 10 characters is suddenly 2 hours. Okay, well, that's a little bit on the threshold of what could be feasible tactically, while I'm on site in an engagement. But if you get it up to 11 characters, so that's like the magic threshold, right? It's up to 48 hours and 3 minutes. And because it is 48 hours, I didn't need my laptop calculating these experimental results for 2 days, so we actually just went with the estimated value there. So it might have been a little bit more or a little bit less, but you can see clearly that there is a threshold between 10 and 11 characters, where the security is greatly increased if you just increase the minimum password complexity requirements in terms of length, and also include mixed case, lowercase, digits, and special characters. So the final thoughts, what are the takeaways from all these crazy numbers that we generated from all of this? I think it's time that we kind of reevaluated what we define as the minimum required password policy length requirements. And based on what we can see from this slide, 11 characters should probably be the minimum. I didn't calculate what 12 characters would look like in terms of the cracking time to rip through all permutations of a 12-character mask, but I know that it would be greater than 2 days, and probably greater than 4 or 5 days even, because like we said, it's not a linear increase, it's an exponential increase. So long passwords are difficult to crack. Increase the minimum password policy length requirements. 12 plus, I think, should be the minimum. And complex passwords, because they're longer, they have an increased key space. So you should also look at your key space requirements. So if you have a web application and you're like, yeah, just require somebody to have a digit, nothing else. Just we don't care about the rest of it. Then you're going to find a lot of users that just have lowercase numbers with a digit appended to the end, and that'll meet the minimum length requirements. But in terms of key space, it's reduced. So that might be a situation where I could crack a 12-character password if I happen to know what these policy requirements were. So the idea is always include mixed case, digits, and special characters because, like we said, length and key space are kings in terms of making a password more difficult, if not impossible, to crack. But this also comes with its own problems. Long passwords are difficult to remember. So this is where we're going to say it is time to ditch the 90-day password change policy that so many corporations and in enterprise environments use. And for a long time, I think this was prescribed. I am guilty of telling clients to do this, long ago. And we started to change that to saying either, make it an annual change or a biannual change. And the reason is, we get into these environments and we see so many passwords that are, a season plus a year, winter 2019, summer 2019. You might see password with just a month and a year, which technically, if you have, all of that, so what are we in May of 19? So just 519, and that way you can have a easy way to remember a password because it's changing so often. So if you change it just annually or biannually, you're going to find that users are requesting less password resets, even if they have a long password. And for your web applications, just consider using the bcrypt algorithm for password storage. I think in most cases, you really won't run into a performance bottleneck with this. If you do, there's plenty of other passwords hashing algorithms out there, but you really want to avoid MD5 and SHA derivatives. They're just not very complex, and they will be crackable. So definitely use bcrypt because, we saw 7-character password is 571 years. So it's a big, big difference. And we really encourage everybody that has attended to try all these things yourself. So Panelizer and InfiniCrypt are all available on my GitHub. You can download Hashcat at hashcat.net. John the Ripper is pretty old at this. It's kind of a dated cracking utility. However, it was the source of our password.lst file, which comes by default with John the Ripper. So that's why that one is on there. And you can also play with John the Ripper. It's just not quite as fast and modern as Hashcat. It doesn't have as good GPU support. And finally, all of the password dumps that we use to analyze in this webinar, as we said, came from Daniel Meisler, SecLists. It's just an incredible repository of anything you could want in terms of hacking resources. So one of the resources they have is the password list, and it's a pretty deep list. You'll be able to find all kinds of things that you wish probably weren't on the internet and so accessible to everybody, but hey, they are, and that's just the way things go. But for everybody that attended, I thank you, and we'll open the floor up to questions.
Thanks, Shawn. Looks like you cover up really good. There is no question for this time. Would you like to add something before I wrap up?
Nope, I think we covered everything, and really I just encourage everybody to go play with these things. Oh, you know what? There is one thing. I mentioned that we really didn't do too much in terms of what are the most common occurring passwords within a domain environment. Those are going to be your winter 2019s and those kinds of things. That would have been interesting to cover, so we might have another presentation that way. But really, anything beyond where we're at now requires data science and not necessarily machine learning, but something called Markov chains, Bayes' theory, just basically linear algebra that kind of go above and beyond what my expertise is in. So we're trying to push this in that direction. The interesting thing is if you look at Hashcat, it actually supports Markov chains out of the box. So a lot of this functionality is already baked into Hashcat. It's just happening behind the scenes, but there's just, excuse me, it's just something much more interesting about going through the process yourself. So it's pretty rewarding. So those are the next steps. So hopefully this is part one of a three-part, or part two of a three-part series on passwords.
Perfect. Thank you so much, Shawn, and great. So thanks, everyone. We appreciate you being here. Thanks again for joining us today. We will see you next time.